Hey everyone, and welcome back to this class. In this section, I'm going to go over some common questions that students have, and some general tips that have helped students in the past. Please keep in mind that this is not a core part of the course. These are just common general questions that students have had about machine learning or about my courses in general. I realize that it's not useful for everyone, but please keep in mind that it's useful for someone. There are a few people out there that tell me they think all the lecturers should only answer their questions, but not anyone else's questions. So just keep in mind that many of your fellow students have asked me these questions in the past. And in order to answer those questions in a scalable way, I've created this section. Please try not to hold it against me, as this may not directly help you, but it may help your fellow students. Please also keep in mind that the Appendix section in no way takes away from the core content. All the material provided for the topic matter is exactly what I wanted to provide. These Appendix lectures are simply extra stuff. So these Appendix lectures do not displace any technical content. If the Appendix section did not exist, the technical part of this course would be exactly the same as it is now. So just remember this: the Appendix is in addition to the technical content. It does not displace any technical content. You get all the technical content that I intended. Also keep in mind that you are always able to select the lecture you want using the user interface. That's this thing. If you don't know how to use the video player to select a lecture, please ask me how on the Q&A or contact Udemy support. So you're encouraged to select the lectures you want to watch manually and skip lectures you don't want to watch. Also keep in mind, however, that a common mistake is in thinking that this material is not going to help you, when in reality it will. For example, I come across students all the time who have no idea how to get started implementing machine learning algorithms in code or why we are doing so in the first place. Then I come to find that they have never watched How to Code by Yourself. So I think it goes without saying that if you don't know how to code by yourself, you should probably watch the lecture How to Code by Yourself. Same thing goes for the other lectures in this section. Alright, let's get to the lectures. Hey everyone, and welcome back to this class. So one question I get very often is, when are you going to release your next course? And when are you going to do your next promotion? The best way to keep track of when I'm releasing courses is to sign up for my newsletter at lazyprogrammer.me. I'm always going to announce things here first, so if you want to be first, this is the place to be. I also give out a ton of free material on my newsletter, so you want to make sure you're signed up for it. I also release coupons on social media, so you want to make sure you're following me on my Twitter. My username is @LazyScientist. Another place I post things a lot is on my Facebook page, so if you want to follow me on there as well, that's facebook.com/lazyprogrammer.me. I'm on various other sites as well, including Pinterest, YouTube, Vimeo, and so on. So if you're already on those sites, just look for me and you'll probably find it. So aside from coupons and announcements, a very good reason for you to be following me on all these channels is so that you can get your hands on exclusive free material. A lot of people make requests, like for example, they want to learn about time series, or they want to use neural networks for regression, or they want to see a TensorFlow implementation of some neural network architecture. If you're waiting for me to add lectures on these topics, it might take a very long time, depending on when I can get around to it. But it's a lot easier for me to write some code and write up a short tutorial. If I do that, there's a good chance I'll release it as free exclusive material, but these are time sensitive, which means I'll offer it for a short period of time and then it will be taken away forever. It's a thank you for being signed up, so if you're not signed up, you won't know and you won't be able to access the material. Finally, a lot of people are interested in coupons. If you want coupons, just email me at info@lazyprogrammer.me and I'll send them to you for whatever course you ask. You don't need to wait for a specific promotion or anything. Just email me personally and I will send you coupons. Hey everyone, and welcome back to this class. In this lecture, I'm going to go over a better way to install data science and machine learning libraries for Python for Windows users. Historically, Windows users have had a lot of problems installing this stuff. Luckily, these days there is an option that makes things very painless and just as easy as they are on Linux or Mac. That is Anaconda. In fact, even if you're not on Windows, you can still use Anaconda. It's nice because it isolates your environment from the defaults provided on your system. So for example, you can have Python 3 in Anaconda, but Python 2 as your system default. When I first started these courses, I wasn't keen on Windows since there were a few essential libraries that couldn't be installed on Windows without a significant amount of effort, if at all. In my view, anything beyond a couple of lines in the console or clicking an install file is too much. And believe me, some students even have trouble with that, so it's good not to make things too complicated before you can even begin the course. Nowadays, that has changed. It's a lot easier to install things on Windows, in large part thanks to Anaconda. And so this lecture is all about how to install all the data science and machine learning libraries you'll need on Windows using Anaconda. So in this lecture, I'm going to walk you through how to install Anaconda as well as some of the libraries you might need that don't already come with Anaconda. You'll find that most of the common libraries such as Numpy and Scipy are already included, so if that's all you want to use, then for you it's just a one-click install. On this slide, I'm going to give you a super short summarized version of this lecture, so you don't have to walk through the installation with me if you don't want to. For some people, that really helps since you can see it, but if you can do it on your own, feel free. So, number 1, download and install Anaconda. This is just a one-click install. It already includes Numpy, Scipy, Matplotlib, and Pandas. That's all we need for the Numpy stack in Python, linear regression, and logistic regression, and a few more courses. It also comes with NLTK, which is what we use for NLP, and scikit-learn, which has some pre-built machine learning models. Now, even though this stuff comes by default, you can still update them if you want. So you can do conda update numpy, for example, and that will update numpy. Number 2, install deep learning libraries. We've got pip install TensorFlow, that's going to install TensorFlow. And if you want to install Keras, you have to first do conda install pip, which is going to update pip, and then you can install Keras using pip install Keras. If you don't update pip first, you might get an error. Next we have CNTK, which is Microsoft's deep learning library. So you do pip install and then the CNTK URL, which you can get from Microsoft's website. So I'm not posting any URL here because the version could likely change in the future, and so you just Google search how to install CNTK and you can get a URL just like this. Next we have PyTorch, that's conda install -c peterjc123 PyTorch. After that we have Theano, so that's conda install Theano, or conda install Theano PyGPU if you have an NVIDIA GPU and you've installed the CUDA toolkit already. Number 3, install OpenAI Gym. That's just pip install Gym. If you want to be able to play Atari games also, then that's more involved, so just skip to the end of this lecture where I walk you through that. If you want to play and save videos using OpenAI Gym, then you also have to install FFmpeg. So the first thing we're going to do is go over to the Anaconda website. That's anaconda.com/download. Scroll down to the Windows section and click on either Python 3.6 or Python 2.7. Or if you're watching this lecture in the future and there's a new version, get that. The code in my courses is compatible with both Python 2 and Python 3, so in that regard, it doesn't really matter which one you get. In the lectures, you might see Python 2 code, but the best way to make sure you're seeing the latest version is to git pull inside the course repo. So make sure you're always doing that because I'm constantly making new updates. Now, although Python 3 is newer, there are still reasons to use Python 2. For example, in your work, you might use Python 2, or certain platforms like Google App Engine only support Python 2. So if you're running a web app there, that means you're stuck with Python 2. It does have great scalability features, so there are many good reasons to use Google App Engine. If you want to get more insight on whether to choose Python 2 or Python 3, just check out the Appendix lecture, Python 2 versus Python 3. So now that we've downloaded the install file, all we need to do is click on it. That's what I mean by one-click install. You click on this, hit OK a few times, and everything is done. Unfortunately, I gave my username a space, which kind of sucks, but that's what happened. So I'm sure some of you have a space in your username too, so if I come across any issues, at least you'll know what to do. Alright, so everything's installed. So essentially everything except the deep learning libraries have already been automatically installed. So you don't need to manually install Numpy, Scipy, Matplotlib, Pandas, IPython, or scikit-learn. So if you're taking my Numpy course or any course that doesn't use modern deep learning libraries, you already have everything you need. So let's go into IPython and make sure that's the case. To start IPython, I go to the Start menu, type in Anaconda, and then this Anaconda prompt application should pop up. Actually, it should pop up before you even finish typing Anaconda. So we go into there, and this brings up a command line terminal. Next, just type in IPython. After that, we can import all the libraries I mentioned earlier. If we don't get an error, that means they've been installed successfully. So let's try something simple like generating some random numbers and making a plot. Okay, so that's a plot of random noise. Let's make a histogram too. Okay, so we see a normal curve just like we expect. Now you can see that TensorFlow is not installed, which is why we get this error. But we can install it very easily by exiting IPython and then typing in pip install TensorFlow. Next, let's try to install Keras. So we get this error. So I looked this up and determined that we need to update pip. So let's do that by typing in conda install pip. Conda kind of works like pip in that way. They are all just tools for installing stuff. Okay, now let's try pip install Keras again. Alright, so everything works. Next, let's try to install NLTK. This is used in my NLP courses. So it looks like it's already installed, so there's nothing more to do. Just keep in mind, if we come across a library you don't care about, feel free to ignore it. I find it's useful just to install everything at the same time so that when you're deep in the code later, you don't have to think about stuff like this. So the next thing we'll install is CNTK. This is Microsoft's deep learning library. Notice how it's not part of pip, so you need to grab the URL manually from Microsoft's website. Unfortunately, it's a little hard to find because there are many pages that deal with how to install CNTK on Microsoft's website, but what you're looking for is a page that has a link to a WHL file. So copy and paste that after pip install. This is a good example because it shows you another way you can use pip by doing pip install and then a URL. Next, let's install PyTorch. This requires us to use a custom source, so we have to specify the option -c peterjc123. So that's conda install -c peterjc123 PyTorch. This is because a very nice guy called peterjc123 has provided us with a version of PyTorch that works on Windows. Now once that's all done, we can verify that they've been installed correctly by going back to IPython. Alright, so TensorFlow works, Keras works, NLTK works, CNTK works, and Torch works. Next, let's install Theano. Theano has historically been pretty difficult to install on Windows, but nowadays, that's not the case. So if you go to their website, you'll see a bunch of instructions. If you don't want to use the GPU or you don't have a GPU, then the instructions will be very easy. I don't have a GPU on this machine, so I'm going to do the easy version. Keep in mind that Theano is really great for learning purposes, so it's totally fine, even if you have a GPU, to just install the CPU version for now and then use the GPU version of TensorFlow. Now I ended up upgrading MKL service and libpython since that's what they told me to do on Theano's website, but it looked like these were already installed. In fact, updating MKL service gave me an issue later, so we'll have to fix that. So if you want to install Theano for CPU only, that's conda install Theano. If you want to install Theano for the GPU, then do conda install Theano PyGPU. Now let me go into IPython and check if Theano works. So we get an error because of this MKL service thing that I mentioned earlier. So let's set this environment variable it's telling me to set. By the way, this is great to know if you don't yet know how to set environment variables on Windows. We can also check that it worked by using the echo command. So let's try that again. Let's do a simple example of adding two numbers in Theano, just to make sure everything's working. If you want to do something even more complicated, you can run this script from Deep Learning Part 2, which doesn't require any external dataset. So just go over to the folder ANN class 2 and type in python gridsearch.py. So that's going to look for hyperparameters using cross-validation. Now in this last section of this lecture, we're going to talk about reinforcement learning. When we start studying reinforcement learning, there is yet another library we'll need to install called OpenAI Gym. If you don't plan on learning reinforcement learning, you can skip this part of the lecture. This has also historically been very difficult, but luckily the open source community has put in the work so you don't have to. You're welcome to read through the GitHub issue on this if you want, but I'm going to just do the simplest thing that works. So let's first do pip install gym. Great, so that worked. Now the second command is a bit longer, so let's go to the actual GitHub issue and copy and paste the command. The easiest way to get there is just to go to Google and type in install OpenAI Gym Windows Anaconda or something along those lines. So let's paste that in. And notice how it fails since I haven't yet installed Git. So we can install Git by doing conda install Git. Now let's try it again. Unfortunately, this fails again because we need GCC, which is a C compiler. Now, one way to get GCC is to do conda install m2w64 toolchain. But unfortunately, I tried this and it also doesn't work. In fact, I think this toolchain was installed already. So I tried quite a few things that didn't work. So in order to save you some time, I'm going to recommend you only try the stuff on this page if everything else doesn't work for you. So what worked for me was to just grab the precompiled binary directly. Now in order to do that, you'll want to go to Cojoli's GitHub repo directly. So that's this URL here, github.com/Cojoli/Atari-Pi/releases. Next, you'll want to download the WH file that matches your environment. So I have Python 3.6 on a 64-bit installation of Windows, so this is the file I want. Luckily, we already discussed earlier in this lecture how to install a WH file. That's just pip install and then the path to the file. So let's do that. Now we can test our installation by running a script that requires an Atari game. So let's cd over to rl2 and then Atari, and now let's run dqn_tf.py. Cool, so everything's good. Now the final thing we want to do for OpenAI Gym is if you want to play a video or save a video, you want to install ffmpeg. So to do that, you want to type in conda install -c menpo ffmpeg. Once you've done that, you can go to the cartpool folder and type in python saveavideo.py, and this will run a script that will play the cartpool game, show a plot, and then save a video. And of course, you can also play this video by just navigating to the file and clicking on it. So for now, that's everything. If I need to add new libraries or updates to this lecture, they will be appended at the end. Hey guys, in this lecture I'm going to show you how to set up your development environment so that you can follow along in these courses. First, let's talk about operating systems. The three big ones are Windows, Linux, and Mac. Most, but not all of my courses are part of the deep learning series. Eventually, the deep learning models we're going to build will become so complex that we will need specialized libraries like Theano and TensorFlow to implement them. Now, as of today, Theano and TensorFlow are not officially supported on Windows. So if you are interested in deep learning, you will discover pretty soon that there is not much you can do without a ton of work. Even working with non-GPU enabled libraries like Numpy and Matplotlib can be a challenge, but these are at least possible on Windows. If you really must use Windows and have your Python environment inside Windows, and you don't want to try the virtual machine method, which I'm going to discuss next, then one good library I know of is called Anaconda. You can get Anaconda at continuum.io/downloads. I can't vouch for this 100% because I haven't used it myself, but I've known others who have found it at least usable. Now I'm telling you this from experience. I've worked with a ton of clients one-on-one, and Python development, especially when it involves the Numpy Scipy stack, is not easy when it's on Windows. The method I'm going to describe using virtual machines will work on most modern computers, and as of right now, if you want to do any deep learning stuff, whether that be with Theano or TensorFlow, you cannot do this on Windows. With that out of the way, I'm going to quickly go over which courses I've released so far or plan to release in the near future that do not require Theano and TensorFlow, so it's possible to do on Windows. With these in mind, you can decide if you want to install a virtual machine or not, but I would highly recommend it because it's free and everyone can follow the same instructions. So we've got linear regression in Python, logistic regression in Python, which are the prerequisites to deep learning part 1. Then we have deep learning in Python part 1, which is mostly in Numpy and a little bit of TensorFlow. We've got easy natural language processing in Python, data analytics, SQL for noobs, beginners, and marketers, cluster analysis and unsupervised machine learning in Python, and unsupervised machine learning, hidden Markov models in Python. This course is going to have a little bit of Theano in it. Next, here are some courses that depend heavily upon Theano or TensorFlow or both. We've got practical deep learning in Theano and TensorFlow, convolutional neural networks in Python, unsupervised deep learning in Python, and recurrent neural networks in Python. As you can see, a lot of interesting and complex stuff can be done in Theano and TensorFlow. Alright, so hopefully I've convinced you that using a virtual machine is a good idea. Windows is a great operating system, but it tends to not be as developer friendly since it tries to be more consumer friendly. Note that if you're on a Mac, this probably isn't necessary. You can just install Numpy, Scipy, Pandas, Matplotlib, Theano, and TensorFlow using easy installer pip. Sometimes this stuff can fail depending on the many combinations of versions of each thing that are possible, but usually just Googling your error message will lead you to the right solution on Stack Overflow. If you're on a Mac, you can just do sudo pip install Numpy, Scipy, IPython, Pandas, Matplotlib, and Theano. Alternatively, you can use easy install, which might have a more recent version. You may need to use easy install to install pip itself, which is just sudo easy install pip. If you want to install TensorFlow, just copy the command at tensorflow.org. It's just a pip install command that points to their custom installation location. I won't put it here since it corresponds to a specific version, and that version may become out of date by the time you watch this. That is good news because the people working on TensorFlow are updating it all the time. Alright, so if you've made it this far, that means you want to install a virtual machine with Linux on Windows, or that you're already using Linux and you want to know what commands to use to install these libraries. We are going to need two things to start for this tutorial: VirtualBox and a lightweight version of Ubuntu. I would recommend Xubuntu or Lubuntu. I'm going to use the 64-bit version of Lubuntu for this tutorial. So download these first and then return to the tutorial. Alright, so now that you've got VirtualBox installed, we're going to create a new machine with 64-bit Lubuntu. So you want to hit New, type in a name for your machine. And this stuff is already correct. I'm going to choose 2 gigs of memory. You can choose more memory if your computer has more memory. I'm going to create a virtual hard disk now. I'm going to choose dynamically allocated, and 8 gigs is good enough for this example. Alright, so I'm going to go to settings. If we go to storage, you can choose the ISO file that you downloaded. So I'm going to load up the Lubuntu ISO that you downloaded from lubuntu.net. Alright, so hit OK and hit start. Okay, so it's going to take you through the installation of Lubuntu. So you want to hit install. Alright, so Lubuntu is going to take you through some prompts. Alright, so you want to erase disk and install Ubuntu, and I'm not going to check any of these. Just hit continue. Alright, so once that's done, it's going to ask you to restart. So just hit restart now. Alright, now that you're in the machine, what I always like to do, if you notice how this window is too big for my Mac window, you can make the inner window resizable by installing guest editions. And this also lets you do useful things like cut and paste between machines. So you want to open a terminal. You go to System Tools, select LX Terminal. Now I'm going to cd into that folder. Cool, so the correct command was sudo /vboxlinuxeditions.run. Notice how there was something that failed in there, so we need to install GCC. So you want to run sudo apt-get update, and then run sudo apt-get upgrade. So the next thing is you want to sudo apt-get install build essential. All right, once you've done that, we can try to run VBox additions again. So that's sudo /VBox Linux. All right, so everything worked this time, so we're going to restart this machine. All right, so now the window is only as big as I want to drag it. Okay, so now we can install the actual data science stuff. So you want to open again LX terminal, do a sudo apt-get update again. Now you want to install, it's a long list, so Python Numpy, Python Scipy, Python Matplotlib, IPython, Python pip, Python dev, and Python setup tools. Just hit yes. All right, so now that that's installed, you can test it out. You can type in IPython. So IPython is open. Import NumPy. NumPy is working. Import Scipy. Import Pandas. Right, we don't have Pandas yet. We will install that next. Import Matplotlib. Cool, so we have everything we've installed so far. So now we're going to install Pandas and Theano. So that's pip install -- upgrade Pandas Theano. Alright, so now we've got Theano. The last thing we need is TensorFlow. To get this, you guys want to go to the TensorFlow website and just grab the latest command, since they're updating the package all the time. So let's open a browser. Let's search for install TensorFlow. Alright, so you take this code, copy it, you paste it into here. Alright, now you've got Theano and TensorFlow. You can test them out. Go to github.com/lazyprogrammer/machine learning examples. Alright, so you need Git if you want to check out this code with Git. So let's install Git. Alright, so let's run our clone command again. Let's try the HTTPS version. Okay, so this one works. Alright, so use cd into machine learning examples. Go into ANN class 2. So this has some introductory TensorFlow and Theano code. So just run Python theano1.py, since this does not require any data. Cool, so it seems everything is working. Now let's try the TensorFlow example. So it's TensorFlow 1. Alright, so you want to make sure you install the correct TensorFlow. You want the CPU only version. Hopefully it just overwrites the other version without any trouble. Cool, so let's try the example again. Super, so now everything is working. Now if you want, there is a text editor that I highly recommend. It's called Sublime Text. So you hit download. You go to Ubuntu 64-bit. You save this. And it will automatically be installed. Alright, so now you have the exact same text editor that I use in my lectures. So you open machine learning examples, and this is all of our code. Hey everyone, and welcome back to this class. This lecture is about how to write code independently when you're doing machine learning. You always hear me say that the first thing you should try to do when you learn an algorithm is to go and write it up in code by yourself before looking at someone else's code. For some students who are new to machine learning, it's not quite clear how to do that. So this lecture is going to explain the thought process you should go through in hopes that it encourages more people to try to code by themselves. I like to encapsulate this in the phrase, when it's time to code, you must code. So remember this whenever you see some code that demonstrates the concepts we learned in this course. Even if you don't fully understand what's going on, coding and copying examples from others helps you build muscle memory. Sometimes people act like they are going to learn tennis by reading a book about tennis. This is of course obviously not possible. You need to learn some things about tennis which are pure fact and reside in your brain as conscious facts. But then you have to go out and practice those concepts on the tennis court. Once you've exhausted and mastered everything you know so far, then you can learn new techniques. So you have this continuous cycle of learning new techniques and then practicing them. Why is this? Because learning the technique as pure fact doesn't mean you truly understand it. Practicing the technique helps you think about the technique from a different perspective. Practicing again and again leads to new understanding, to learning in the subconscious, which is muscle memory. You must go through this cycle. But some students naively think they are going to read an entire book about tennis and then be a tennis master the first time they try playing. This is very common, especially when all you really need to do is sit there and watch a video and no one can force you to type. A lot of people don't even think to try. So just remember this whenever you see code. When it's time to code, You must code. First, we are going to talk a little bit about why you want to code by yourself. A lot of the time, what an algorithm does or how it works isn't quite clear the first time you learn about it. Every individual will have their own unique background, so they might be familiar with the patterns and know exactly what to do, while some individuals might have questions that no one else has. Sometimes you gloss over details because you assume you know what's going on, when really there are important things you're not considering. So this is how trying to code by yourself can help you. Coding by yourself forces you to think about each and every detail. It forces you to think line by line. You have to be familiar with the data types and the shapes of all your variables, and they all have to fit together properly, kind of like Lego blocks. As an example, you know that in order to do element-wise matrix addition, both matrices have to have the exact same shape. So if you find that they are not the same shape, then one of your previous assumptions was incorrect. So you should go back and correct it. Lego blocks have to follow a specific set of rules in order to fit together properly. If you make incorrect assumptions about how Lego blocks fit together and you try to join them, it's not going to work. Without trying to build things by yourself, you will never discover these details. Let's now talk about how to code by yourself. Consider the supervised machine learning scenario. We know that we're going to have some inputs and some targets, and we want to try to make predictions from the inputs that are very close to the targets. We typically call the inputs X and the targets Y. Sometimes we call the targets T, but for the purpose of this lecture, we'll call the targets Y. Now this next point is a key point. It doesn't actually matter what X is and what Y is. It doesn't matter if you're looking at an e-commerce data set, and the columns of X might be time on site, time of day, how many pages the user looked at, and so on. You could just as well be looking at a data set of X-ray images, where each column is the pixel intensity of an image. This is the key point. We say all data is the same. When we do linear regression, we don't have different kinds of linear regression for e-commerce and X-ray images. Linear regression is the same algorithm no matter what your data set is. So we say all data is the same. Theoretically, I could give you a data set of X's and Y's, and you could train a classification algorithm on it without me even telling you what the X's and Y's mean. You should get very comfortable with this idea. Sometimes people say, well, this isn't practical because I want to do concrete examples. But that's because they're not thinking intelligently. In fact, this is the most practical thing we can do, because it means everything we learn, we can apply it to any data set that exists. It means that I can train a model on an e-commerce data set, but I can also train a model on an online advertising data set without learning anything new at all. It's truly the greatest form of lazy programming. Learn something once and apply it to every industry. One great consequence of all data is the same is that there is an unlimited amount of practice opportunity for you. You can download data sets from Kaggle, from Google, from Wikipedia, from Amazon, or from anywhere else and try the algorithms you learned. What this means is, let's say you have a data set you care about more than something we do in class. See, in class we have to use data sets that everybody can understand. For example, text and images. Everybody should know what text and images are. Text and images are just fundamental data types on the web. You probably don't even think about the fact that text and images are data because it's so trivial. In any case, we work with text and images a lot because everybody understands them. But let's say you're a biologist and you know about DNA. You find DNA and genomics really interesting. So you want to use the algorithms we learn on that. Well, that's great and you should totally do it. Remember, all data is the same, so all you need to do is convert your data into the appropriate X's and Y's to plug into our machine learning algorithms. The downside is, we most likely won't talk about DNA in class unless it's a very simple example, because most computer scientists are not biologists too. So they don't know what DNA is. They don't understand the specifics. So an example wouldn't make much sense to them. This is opposed to text and images, which makes sense to everybody. Same goes with any other specialized field like finance, computer networking, cosmology, and so on. So now we can start off from the right place to talk about supervised learning. We have our X's and we have our Y's. What do we do with them? In supervised learning, we know that there are two main things we want to do. We want to do training and we want to do prediction. In scikit-learn, all the models have the same API. It doesn't matter if you're doing logistic regression or decision trees or random forest. All supervised models in scikit-learn have the same two functions, fit and predict. Fitting a model is just a synonym for training a model. If you don't believe me, you can go look at the scikit documentation yourself. When you're learning about supervised machine learning, what you're really learning is what goes inside these two functions. What are the parameters and how are those parameters learned? That's really what all supervised machine learning is, filling in these two functions. Taking this perspective is going to give your code structure, and it's going to make things much easier to visualize in your head. Let's now do a simple example to solidify this idea. In this example, I'm going to give you an algorithm and you will implement it in code. There are two key points I want to make before I give you the algorithm. First, I'm not going to give you much intuition about how it works. Second, I'm not going to derive the theory behind why it works. The reason I want to mention these two key points is that you should realize you don't need these two pieces of information in order to translate pseudocode into code. A lot of time, these three concepts, intuition, theory, and implementation, work to reinforce each other. The reason I'm focusing on implementation right now is because it's the one people most often miss or think they don't need at all, when really it's an extremely important part of the learning process. Okay, so the pseudocode is as follows. In my predict function, as you already know, I'm going to take in some input data x. My predictions will be y hat equals x times w. You might already recognize this as linear regression. However, forget what you know about linear regression and pretend that this is just some formula I gave you. What I can tell you is that we are creating some kind of regression model. It should be clear from this equation that the parameters of the model are contained in this vector of weights w. I would probably also tell you that w is a vector that's the same size as the number of feature vectors in X. Of course, this must be true in order for the matrix multiply to be valid. This acts as kind of a sanity check so you can make sure everything is making sense. In my fit function, I want to perform this loop some number of times. Since we know from the previous slide that the parameters of the model are contained in w, then it should be clear that inside the fit function, what we want to do is update w. Not surprisingly, that's what's happening here, another good sanity check. Now, because you're already familiar with linear regression, you probably already recognize this as gradient descent. Again, I want you to pretend that you don't know that. But what do you know? You know that iterative algorithms are common in machine learning, and that gradient descent is among the most common. You could probably infer that this is some form of gradient descent, but you don't need to know what it is in order to write it in code. What else do we know? You know what a for loop is, and you know how to write one in Python. You know that X is an n by d matrix containing the input data, and that y is an n-size vector containing the targets. You know that y hat is an n-size vector containing the predictions. You know that w is a d-size vector containing the model parameters. And you know how to add, subtract, and multiply these objects. So we can write this algorithm without even knowing how it works. Of course, a lot about how it works can just be inferred from this formula. Here is what you don't know. You don't know t, the number of times the loop is supposed to run. You don't know eta, the learning rate. This is completely fine. You can't let this lack of knowledge stop you in your tracks. The truth of the matter is, there are going to be situations where you're not told the exact numbers to plug in. In many cases, the answer is going to be, it depends on the problem. The important thing is, you have to get used to the idea of trial and error, and you have to make educated guesses based on what you already know. So what can you do? Well, you know that the learning rate is supposed to be a small number. How small? It depends on the problem. Typically, it's a number less than 1, like 0.1. If that doesn't work, you might try lowering it. Typically, we lower it by factors of 10. So for example, the next learning rate we would try is 10 to the minus 2, 10 to the minus 3, and so on. Typically in machine learning, whether you're looking at a supervised or unsupervised algorithm, there is an associated cost or objective function that you're trying to minimize. Let's suppose I tell you it's squared error, which is typically what we would use for regression. Well, now you have a way to choose the number of iterations of the loop and the learning rate. How do we do this? So inside your fit function, you would plot the cost as a function of iteration. I always recommend doing this no matter what algorithm you're looking at. In general, you always want the cost to converge. The pattern you typically see is that there is a steep drop at the beginning and it slowly flattens out as the number of iterations increases. To choose the number of iterations, you want to stop when the curve is sufficiently flat. You might recognize this as a diminishing return scenario. The returns diminish because at the beginning, we reduce the cost by a lot in just a few iterations. At the end, we can do a lot of iterations, but we reduce the cost by almost nothing. An alternative is you could use a separate validation set and stop when the validation cost increases, but that is not the focus of this lecture. Unlike the training cost, the validation cost is not guaranteed to decrease at every round because that is not what we are minimizing with respect to. You can also use this same plot to help improve your learning rate. If the cost explodes or becomes not a number, your learning rate is probably too high. If your cost converges too slowly, you can try increasing your learning rate. So what does your final code look like? Well, we know we want to create a class with at least the predict and fit functions. You don't have to use a class, but I find that it encapsulates the code nicely and provides useful structure. Notice that once you have the algorithm in math, there isn't much work to convert it into Numpy code. You know how to do matrix multiplication, you know how to add, you know how to subtract. These are basic arithmetic operations that I'm sure you know already. If you don't know how to do these in NumPy, then I have a completely free NumPy course on the NumPy stack that you can take. Here is the second part of the code where we actually create an instance of the class and then use it. I've also included the squared error cost function just for completion's sake. What's cool about this template is that it doesn't really change from one algorithm to the next. The structure is basically always going to be this way, at least for supervised learning and unsupervised learning. So as we discussed before, it doesn't matter what algorithm you're implementing, whether it be linear regression, logistic regression, a neural network, and so on. They always have the predict function and the fit function. And learning what goes inside these functions is equivalent to learning the algorithm. So in fact, one way to begin coding is to start with just this boilerplate code and then fill in the blanks. This is what is known in software engineering as test-driven development, or TDD. In test-driven development, we start by writing tests because number one, your code should always have tests, and number two, writing the test first forces you to think about how you expect your API to work, and it allows you to make sensible design decisions without being distracted by implementation details. So you see how this applies to every machine learning algorithm, not just linear regression. In a lot of my older coding videos, I unfortunately decided to just write the code straight through. This helps some people, but is not ideal for others. In addition, the coding videos will appear without warning. Generally, the lectures appear in the same pattern. First we do theory, and then we do the corresponding code. It pretty much always works this way. So after the theory lecture, you can be pretty sure we are going to implement that theory in code soon, unless it's so simple that it can be an exercise. Now, to avoid treating everyone like they're in kindergarten, I don't have videos telling you that it's time to code. You're all proactive and independent adults, so when you learn some theory, you already know that it's time to try to put that into code by yourself. Sometimes you might get stuck and have no idea what to write in code or what the data set is. In that case, it's fine to watch the next coding lecture, but don't watch it all the way through. Watch just enough so that you know what the general idea is and what we're trying to accomplish, and then try to finish the rest yourself. Now let's say you've watched just enough so that you know what we're trying to do. You know the theory, but you still can't complete the code. At this point, you may want to revisit the lecture theory to make sure you really understood each part. Failing that, you may want to try and get clarification on the discussion board. Failing that, you may want to look at external resources as well. Sometimes you might be missing some important computer science background that I've assumed everyone already knows. That's perfectly fine because everyone has a different background. It's highly encouraged to do your own research, and this is also perfectly normal. It's not a bad thing, it's a good thing. Ask any university student if this is what they do, and they'll tell you that they do it all the time. This builds a level of mental toughness and initiative taking that's important if you want to learn this stuff. There's a lot to learn, and I myself am still learning new things every day. So let's say you've rewatched the theory lecture, you've looked at some external resources on the theory, and you still don't understand how you would put it into code. Well, at this point, there are some great exercises you can do. Watch the coding lecture or look at the full code on GitHub. Go through it and make sure you understand each line. The next step is, without looking at the code again, try to implement it yourself. This by itself is a great learning tool. Many of the algorithms I've learned, I didn't understand them the first time. I learned them by looking at someone else's implementation and dissecting it. I looked at each part and I asked myself, which parts did I get right and which parts did I get wrong? This helps you understand the mistakes you were making previously. The cool thing about implementation is it works backwards too. We go from theory to code, but thinking in the reverse direction, the code actually helps us understand the theory better also. I always say that if you can't implement the code, then you don't understand the theory. So if you can learn the theory 50% of the way, try to implement the code, look at an existing implementation, and then finally get it working, then you can be guaranteed that you now know more than just 50% of the theory. The act of coding helped you understand more of the theory than if you had just learned the theory by itself. So implementation helps you understand the theory, but it also helps you understand the intuition as well. Intuition is a tricky thing. In fact, I would go so far as to say it's a trap. In many or maybe even most cases, intuition is built on experience. That means deriving the theory from first principles, or in other words, deriving the theory from facts you already know to be true, and from implementation. Students often want to hear intuition from people with lots of experience, but the problem is that this intuition is built on hindsight. Intuition is often both the first thing and the last thing you want to focus on. You want to have a little bit of intuition at the beginning, so you have some general idea of what you want to accomplish. Then after you learn the theory and implementation, you can reflect on the details and summarize them at a high level. This is real intuition built on hindsight and experience. The big mistake beginners make is that they read some intuition written by someone else who actually has experience when they themselves do not. From an outsider's perspective, it's hard to tell the difference. Why is that? Well, if the beginner can regurgitate the same high-level ideas as the expert, then it would sound like they are also an expert when in fact they are not. There are unfortunately too many courses out there that do this. They want you to feel good that you learned something, and they want to avoid you having to do anything too difficult. And because you can repeat the same high-level intuitions, it actually sounds like you're an expert. So this is why I call it a trap. Knowing intuition not only makes you feel like you know something, it also makes you really confident about this fact. And then because your ego wants to maintain this confidence, you'll start making crazy statements like the theory and implementation are not important because you already understand the intuition. But as you know, this is completely backwards. Let's summarize this lecture, since that was a lot of information to take in. Remember, this lecture is all about how and why you should code by yourself. First, we talked about why. This is because it ensures you are thinking about the details and filling in the blanks using your own pattern recognition skills. It ensures you don't just assume you know what's going on, but that you actually know what's going on. There's a big difference, especially if you're the type of person that likes to assume you know everything. Next, we talked about how. We talked about how all data is the same, and it doesn't really matter what domain or industry your data is from, the same algorithms all apply. Next, we looked at the interfaces to the algorithms, which are also conveniently all the same. So we have a kind of mix and match type of scenario, where we can input any kind of data into any kind of model. For example, you can use linear regression with financial data, or you can use a neural network on ecological data. All data is the same, and all models have the same interface. Next, we talked about a strategy for how to actually apply this. You've probably already seen that we always alternate between theory and code. First, we discuss the theory, and then we implement that in code. Sometimes you might have to go back and revisit the theory, or sometimes you might have to look things up on the internet. That's perfectly normal. This is pretty much the day in the life of a university student. We're trying to build the same level of mental toughness and initiative taking in this course. So the strategy is, stop after you learn the theory and try to code yourself. Sometimes you need a little more detail, so you might want to watch a little bit of the coding lectures to see what's going on, and then try to implement the rest yourself. If you can't get it by yourself, then maybe try watching the whole thing, or looking at the expected result, and then trying to implement it from memory. This by itself is a great learning tool because it allows you to ask yourself, what did I get right and what did I get wrong, so you can understand the mistakes you were making. Finally, it's important to understand the difference between intuition, theory, and implementation, and how they reinforce each other. It's important to not fall into the trap of only understanding intuition, written by someone else, and then assuming that this equates to actually understanding everything. In many cases, it's not about waiting for someone to tell you some nice phrases that trick you into thinking you understand the intuition, but rather you should seek intuition by working through the theory and the implementation. And lastly, don't forget, when it's time to code, you must code. Hey everyone, and welcome back to this class. This is a short lecture I like to give in each of my courses on how to succeed in this course. This is very important to talk about because you're learning a difficult technical subject. It's easy to get stuck, or even worse, give up because you're just not getting things. Maybe there are too many gaps in your knowledge, so you can't connect the dots. Maybe some assumption you've made is incorrect. And keep in mind, there's a lot of material in this course. It can be overwhelming if you're new to this field of study and you're not familiar with the conventions and the typical patterns we use. Now, if you've already seen this lecture in the past, you are more than welcome to skip it if you remember what's in it and you're already using these guidelines. The first guideline is this. Remember that I want you to succeed. In fact, that's why I'm giving you these guidelines in the first place. So if at any point when you're watching these lectures and you become confused, just ask on the Q&A, also known as the discussion forum. Typically, I respond within hours, sometimes even within minutes if I happen to be on the site and I see a notification. I answer any and all questions, so even if you think it's stupid, just ask anyway. One example I get from time to time is, where do I get the code for this course? And of course my answer is typically, well, it's in the lecture called Where to Get the Code for This Course. At the end of the day, no one cares if your question was trivial or silly. If it's something keeping you from progressing in the course, I want to answer it. Now, very rarely I get people saying, well, I was so confused that I couldn't even think of the right question to ask. And this is where you have to take some responsibility for your own learning. You have to ask yourself, what did the instructor assume I know that I didn't actually know? Maybe I can look into those things, and that will help me formulate a question. Maybe there's some background knowledge I'm missing. A lot of people like to have exercises to practice when they're taking a course. The act of thinking of the right question to ask is itself an exercise. It might not be the type of exercise you thought you'd be doing, but in many ways this is more profound. This is an exercise that requires you to think and to change how you think. And ultimately, that is the best value you can get out of a course. Speaking of background knowledge, this is one of the most important guidelines in this lecture. You may have noticed that in the course description, I've listed some prerequisites, or in other words, things you should know before starting this course. Now you might wonder, why do I ask you to know these things? Why don't I just teach them in the course? And while we do review some topics in this course, it's not the focus. There's such a wide variety of students in this course. Students from almost every country in the world. Students of all ages. Students of all backgrounds. What does this mean? That means what's review for one person is going to be totally new for another. Some people are going to tell me they don't know calculus. Some people are going to be very far behind with their Python programming skills. But if we start teaching Python programming skills, other people are going to say, hey, why are we doing Python? Isn't the topic of this course deep learning? And I tend to agree that we should stay on topic. So how can we reconcile this? Well, it doesn't make sense for me to give you an entire computer science education in this one course, because a lot of that would be irrelevant for a lot of people. The only logical thing to do is for all of us to meet at a common meeting point. How is that point defined? Well, it's defined by the course prerequisites. In fact, they are so important that in certain instances, I've listed the course prerequisites twice, just in case you missed it the first time. And I'm also reminding you now for good measure. Now, one pitfall is that people sometimes assume they know things that they don't really know. So if you took calculus 20 years ago and you got a C, and you skipped class, and the times that you did show up for class you were sleeping, well, probably you don't know that much calculus. But remember, I want you to succeed. I want you to be able to learn this material. I can point you to resources where you can pick up this missing background knowledge, but the key is you have to ask. In some cases, there are certain places where I'm not allowed to post certain links, so we have to be mindful of the rules of the platform we're using. Now, occasionally people ask me, well, why don't you just teach a course for pure beginners? Why don't you teach these courses in such a way that they don't require lots of math and lots of prerequisites? Well, I don't want to turn this into an easy beginners type of course, because for one, that's not what I'm interested in personally. And number two, don't forget that this is state-of-the-art stuff. State-of-the-art generally isn't easy, and if it were easy, that would mean everyone is doing it. And if 1,000 other people can do the same thing as you, well, what's a potential employer going to think? What are your chances of getting that job when all 1,000 of you have the exact same skills? So we don't want skills that are easy to get. We want skills that are hard to get. Skills that put you at the top of your game. Skills that not many people have. If I'm hiring someone, I want the guy who stands out, not the guy who says the same thing as everyone else. Finally, the final guideline for how to succeed in this course. I mentioned earlier that there's a lot of material, so much that it can be hard to keep track of. In addition to taking your own notes and doing all the derivations yourself, how can you be absolutely sure you're understanding this material? I would in fact consider this even more important than the derivations. Not everyone is going to be a pro at math, so it's understandable if you want to skip a few steps. Sometimes it's possible to compartmentalize some concepts or delegate learning them for some other time, but still understanding the high-level picture and how it fits in with everything else. What you cannot skip is the implementation. Implementing these algorithms in code, is the real test for whether or not you understand the material. And this is not about reinventing the wheel or that you shouldn't roll your own whatever because someone else out there can do it better than you. That is a software engineering principle, not a principle of learning. In production, you don't want to write your own hash map or your own string class. And yet, what do we usually do as an exercise in a typical intro to computer science class? Well, we do precisely that. We implement hash maps and we implement strings. And why do we do this? Because we want to have a better understanding of how these things work. If you make an assumption that's incorrect, well, your code is probably just not going to work. Merely using a hash map and using a string only gives you a very superficial understanding. That's beginner stuff. That's stuff everyone knows. That's not stuff that's going to help you stand out from the competition. And it's true that you'll never use your own homemade hash map or your own homemade string in any code you write, unless of course you are a professional that focuses on that sort of thing. They'll probably be inefficient and they'll probably have bugs, but that's okay because you're not doing it to make it perfect. You're doing it to learn. You'll notice that the general pattern that this course follows is that we always discuss theory and then we implement that theory in code. So we're always going from theory to code, implementing everything that we learned. If you can, try to implement something before watching the coding lecture. In the appendix, I have a lecture called How to Code by Yourself that goes much more in depth into this topic, along with multiple strategies for how to approach implementation exercises. So to summarize, these are the guidelines I think are going to help you succeed in this course. Number 1, make generous use of the Q&A, even when you can't think of the right question to ask. Number 2, make sure you meet the prerequisites to this course. If you're not sure what they are, or you're not sure how, see guideline number 1. Number 3, try your best to implement everything we learn. This is the true test for whether or not you understand something. Remember that it's perfectly normal to get stuck once in a while. I get stuck all the time when I'm learning. That doesn't mean I'm not smart, nor does it mean the book or video I'm learning from is bad. It means that there's a disconnect between what the author believed I knew and what I actually know. And as a learner, I do my best to close that gap. A good skill to have is learning how to compartmentalize concepts. So here are the things I understand, here are the things I don't understand, but here are the things I understand about the things I don't understand, and these are the holes. So you know what you're missing and you know where they fit, and you can work to fill in those gaps over time. One thing I've been doing quite a bit recently is adding review lectures to my courses. These aren't meant to teach you everything from scratch, since that's going to take you a long time, but they are meant to help you recall certain things you may have forgotten. So if you have an idea for a review lecture that you'd like to see added to this course, please feel free to make a suggestion using the Q&A. Hey everyone, and welcome back to this class. This lecture is designed to answer some common questions I get about how difficult this course is and where it fits in terms of academia, the professional world, and its practical applicability. So rather than answering this question individually over and over again, it seems like a better idea to make a lecture about it and answer everybody at the same time. A lot of people become confused because this is their first machine learning course and they just don't know where it fits in the grand scheme of things. So is this course academic or practical? And is it for beginners or experts? Is it fast-paced or slow-paced? I'm going to answer the second question first. Is this course for beginners or experts? Interestingly, the problem with this question is a problem for machine learning too. Let me explain why this question is itself problematic. One of the challenges in natural language processing is that of ambiguity. When someone says some words, the problem is those words can mean multiple things. And it just so happens that I have some courses on NLP, so this is a problem I think about often. So how does that apply here? Well, when we use the words beginner and expert, we have to ask, A beginner from whose perspective? An expert from whose perspective? For some of you, you might think that a beginner is a random person you take off the street who knows nothing. But even that is ambiguous. There are people out there who do not even really know how to use a computer beyond turning it on and checking their email and browsing the web. There are people out there who are pros at Microsoft Office, so they know how to use a computer and make a Microsoft Word document or a spreadsheet, but they've never done any programming before. There are people out there who are very good developers and have lots of programming experience, but they have no idea what machine learning is. So all of these people are beginners in some way, but each of them would require a vastly different amount of work to prepare for this course. It's the same situation with experts. Most people consider anyone who knows more than them to be an expert. But of course, how much you know and how much some other person knows is relative. If you know how to plug and play into scikit-learn and nothing else, you might seem like an expert to someone who only knows Excel, but you'll seem like a beginner to someone who's read Bishop's Pattern Recognition and Machine Learning book. So just to finalize our answer to this question, is this course for beginners or experts? This question is misinformed to begin with because beginners and experts are not well-defined terms. Instead, we have to go back to what is the specific skill set you need before starting this course. And of course, that's defined by the prerequisites which are listed in the course description. So precision is the key here. We want to know what is the precise list of skills that I need before taking this course. This is much better than ambiguous terms like beginner and expert. Another matter is that people are going to measure their own skills differently. That's a much tougher issue to deal with. Sure, I can say you need to know Python coding before starting this course, but you can be sure that there's a big difference between someone who just learned Hello World and for loops versus someone working at a big financial institution. Now, even in those big financial institutions, there could be big gaps in performance. Even within your own team, there can be big gaps in performance. I've seen guys who've been working for 15 years do worse than guys who've been working less than 1 year. So even if I say you need to know Python coding, there can be a lot of variation in skill among those who consider themselves good at it. A similar situation happens with deep learning. I can say you need to know how neural networks work. But there's a big difference between someone who can code them from scratch and has experience using them versus someone who just watched some online animations for a few hours. If you had to bet on who knows neural networks better, who would you pick? So to really answer this question, we have to turn to the course itself. If I say you need to know Python coding and you claim that you do, but you don't understand some Python code in this course, then simply put, your Python coding skills are not yet up to par. So you have to improve your Python coding skills by asking questions on the Q&A and taking the appropriate steps to cover your gaps. Quite often, I get people who are just too confident in their own abilities, when unfortunately the reality is there is a huge discrepancy between what they think they know and what they actually know. What's funny is these people sometimes say, this course requires PhD math. I assure you, there is absolutely no math in any of my courses that requires a PhD or that only a PhD can understand. My courses contain only undergraduate math at most. Sometimes people even claim to have a PhD and then claim that it's still too hard, which is funny because that essentially invalidates your entire PhD. The entire point of a PhD is to turn you into an independent researcher. And so if you're supposed to be at the level of doing independent research, but you can't understand some undergraduate math, well, that's not very good. Essentially, what it boils down to is people are really trying to say, everything I don't understand is not important. Everything I do understand is important, and therefore, everything you say that I don't understand, I don't need to know. You can see why this thinking is dangerous. If you truly believe that everything you do not know is not important, then you'll never learn anything new. Now this brings us to our third question. Is this course fast-paced or slow-paced? And I think you can see where I'm going with this. This is yet another example of ambiguity. Fast-paced to whom? Whether it's fast-paced or not depends on which person is taking the course. So if someone is well prepared, then things will be just right. If someone already knows most of these topics, then it will probably be too slow. If someone chose not to prepare for the course, or they have an inadequate understanding of the prerequisites, then it's going to be too fast. So if I expected you to know something and you didn't, then you have to look it up, which is going to make the course feel like it's going too fast. So here is the real test. If I say something depends on calculus and probability, and you claim to know calculus and probability, but you don't understand the thing that depends on calculus and probability, you have to ask yourself honestly, do I really understand calculus and probability? Or did the instructor invent his own kind of calculus and probability that I don't yet understand? Well, of course, that's not very likely. It's most likely that you thought you understood calculus and probability, but you really don't. Now on to our initial question. What kind of course is this? Is it academic? Is it for professionals? Is it practical? So to understand this, you have to understand where machine learning is usually taught and how it is usually taught. Firstly, machine learning is usually taught in upper year computer science and engineering programs in university and college. So these are students who already took calculus 1 to 3, linear algebra, differential equations, probability and statistics, discrete math, programming, and possibly more, all in their first 2 or 3 years of college. So by the time they get to 3rd and 4th year, they know all this stuff and they're ready to apply it. So a typical academic course might cover a whole library of machine learning algorithms. So you might learn k-nearest neighbor, logistic regression, k-means clustering, PCA, and so on, all in the same course. Typically, you'd cover one algorithm per lecture, which is about 2 hours. Overall, you might have something like 12 or maybe 20 of those lectures in a term. And by cover, I mean mostly via math, geometry, and derivations. These courses don't typically have you at your computer doing programming work. If you do end up doing programming, it's usually part of a lab assignment, which is actually just a very small part of the course, compared to the rest. So it's mostly theoretical, dealing with equations, solving equations, reasoning about equations. Those equations typically involve probabilities and information theory. So you have 2 hours to go through the theory for one algorithm, and then if there's coding involved, which there usually isn't, you do it on your own time. The lectures themselves do not involve any coding. But there's an even bigger problem with these academic courses, and what is that? What happens is that the grades turn out to be very low. Out of 100%, the average might be around 25% or up to 40%. Now you might think, wow, so everyone fails. And of course that's not the case since everyone gets shifted based on the average. So what is the real problem here? A lot of people ask me, well, why don't you cover every machine learning algorithm in one big massive course and just call it machine learning? Well, the answer is that if you try to do too much, you only end up understanding 25% of the material, which I think is clearly demonstrated here. And as they say, the proof is in the pudding. If you look at these courses where students are trying to digest 10 different algorithms at the same time, what is the result? The result is they don't understand any of them. If you try to understand too many things, you end up understanding nothing. I take the perspective that if you're going to take a course, you should aim to understand 100% of the material. Each course is broken up into appropriate levels, based on how difficult they are and by topic. So for example, you can typically take Calculus 1, which focuses on differential calculus, Calculus 2, which focuses on integral calculus, and Calculus 3, which focuses on multivariable calculus. You would never learn all of these in just one huge course called math, because that's just too much stuff to understand all at once. I want you to understand 100% of the material. Even 50% or 75% is not good enough in my opinion. If you only understand 75% of the material, and the next course depends on the 25% that you didn't understand, well then you're not going to make it to the next level. Now let's look at the opposite end of the spectrum, what most people might consider to be a practical course. I don't consider these to be practical courses, and I'll explain why later. But I'll use the word practical here in quotes, since that's what some of the more beginner students will refer to them as. So how does a practical course typically proceed? Well, first, you are never really taught how the algorithms work, other than at a very high level. You might learn how they work by way of analogies and metaphors. So for example, suppose you're learning about gradient descent. Well, the instructor might relate this to a ball rolling down a hill. Now some beginner students, they might conclude that, I understand a ball rolling down a hill, therefore I understand gradient descent. But they neglect to understand how to take derivatives, they neglect to understand how to choose a good learning rate, and most importantly, they neglect how to implement gradient descent in code. So it's totally wrong to assume that just because you can visualize a ball rolling down a hill, that you understand gradient descent. Why? Well, the problem is, everybody can imagine a ball rolling down a hill. Your grandparents who can't even turn on a computer can understand a ball rolling down a hill. So don't equate understanding an analogy to understanding the real topic. So what's the next thing these practical courses do? The next thing they usually teach you is how to plug into an API, or in other words, make use of a library someone else wrote. This is also not ideal. Typically, this involves just 2 or 3 lines of code. You have to wonder, if machine learning just boils down to 2 or 3 lines of code, why is it such a big deal these days? Why did it take decades for people to realize its usefulness? And of course, the answer is that there's much more to machine learning than just these 2 or 3 lines of code. When you use a deep learning library like Keras, you're not doing deep learning. You are using a deep learning interface. You're simply programming. It's more accurate to say, I can program with deep learning libraries, rather than saying I actually know deep learning. But some of you might say, well, that's all I really want to do. All I need is an API, and for the API to give me an answer. I don't care about how it works. But then here is where you run into trouble. Recall that in addition to all data is the same, we know that all machine learning interfaces are the same. So the question becomes, which API do you choose if they're all the same? How can you make an informed choice about which one to use? Well, the reality is, if you don't know how these things work, then you can't answer this question. This is why some of these so-called practical courses can cover 20 algorithms in the same course. It's because they never actually talk about how the algorithms work. Since the API is the same every time, it's very easy to just do the same thing 20 times and then not bother with the details. So this gives people a lot of confidence that they were able to do the same thing 20 times. But it's dangerous thinking because you don't realize you really only learned one thing, you just repeated it 20 times. So how about when it comes to the professional world? Sometimes people tend to believe that in your profession, you'll be leaning more toward the practical end of the spectrum, where you don't really need to know how a machine learning model works, you just have to know its API. But what it really comes down to is what your job actually is. If you're a regular everyday programmer and you just want to see how a machine learning model might perform on your data, then you're going to use a pre-built library most likely. That's just the 2 or 3 lines of code I referenced earlier. However, that does not mean you don't still have to conform to best practices, make sure you're not mixing your test set with your train set, make sure you're doing proper validation, and so on. And when it comes to tuning your model, then you'll have to be able to dig down into the details and see which hyperparameters are possible to change and which are likely to have the most impact. So only knowing how to use an API is only going to get you past the first stage. You can plug in your data and at least your code has the right syntax and doesn't crash. But of course, your code not crashing doesn't necessarily mean it's right. Back on the other end of the spectrum, you have programmers and scientists whose sole job it is to do machine learning. These guys are machine learning experts. They know the math inside and out and have a full computer science education. And so, to even be able to communicate your ideas effectively, you have to be comfortable with the theory and not just how to plug into an API with 2 lines of code. These scientists are building custom models, really digging down into the math to not only use, but invent new things. And to be able to invent new things, you really need to know the math very well. And so if you're on a team like this, you can't just know how to write 2 lines of code. Your skill set has to be far beyond that. So your theoretical background has to be very solid if you want to be able to communicate effectively with other scientists. Now, a lot of people say, well, I don't ever want to be a scientist, so I don't really care how these algorithms work. Unfortunately, that's a very bad attitude to have in the workplace. Suppose, for example, I am running a business. Now, an employee of mine, he wants to show off and say he's learning about machine learning. He says, oh, I'm taking this machine learning course online, therefore I will become a machine learning master. But his approach to machine learning is to learn as little as possible. He says he doesn't care about the math, he only wants the practical stuff. He only wants to know the bare minimum. He tells me he doesn't care how it works, he's just going to plug into some API, because that's what his buddy told him he could do. As a business owner, I really don't want this guy working for me. I run a business that sells something, and the life of the company itself, and the livelihoods of the employees, all depend on our products being the best they can possibly be. So if someone comes to me and says, I don't care about being the best, I just care about doing the bare minimum, my response is, I don't want that guy on my team. In fact, he should be fired. So be careful if this is your approach to machine learning. No business owner wants to hear that your approach to the business is to do the bare minimum and to put off some math because you think it's too hard. That's a scary prospect for a business owner. Now, if we go back to our original question, maybe you've realized we haven't answered it yet. What kind of course is this? Well, you can think of it as a marriage between these approaches. We want to cover all the math and derivations because that's very important if you want to be able to communicate effectively with other scientists, to be able to debug your code effectively, and to be able to invent new approaches. This is also what we mean by machine learning. We mean really knowing machine learning and not just programming with an API. So the theoretical background is very important. At the same time, we're not going to introduce 20 different algorithms in the same course, because unlike a typical academic course where you can pass just by understanding 25% of the material, in this course it's structured in a way that if you have any missing gaps, it's going to be impossible for you to move on to the next stage. But academic courses don't contain much coding, if at all. So in this course, every algorithm we learn about will be implemented in code. My motto is, if you can't implement it, then you don't understand it. You can pretend to understand it, and when you talk about it, you might sound like you understand it, but implementation is the true test. It's like a math exam rather than writing an essay. When you write an essay, you might be able to fool the teacher into thinking you understand something, but in a math exam, either your answers are right or your answers are wrong. In this context, either your code works or it doesn't. It's very clear cut. When it comes to practicality, we cover that too. We demonstrate our algorithms both on real-world data like text and images, and we demonstrate our algorithms on two-dimensional data sets so that you can visualize what an algorithm is doing. Both of these are important. Text and images are quite possibly the most practical data there is. Some billion-dollar companies exist and thrive because of those capabilities. 2D data sets are critical as well because as humans, that's the only thing we can see. But at the same time, we don't try to pull the wool over your eyes and pretend like you need 20 different data sets to practice on. Instead, we learn something much more valuable, how to use an algorithm on an infinite number of data sets, because we are able to abstract the idea that all data is the same. Remember that all the computer sees is a list of numbers. It doesn't know that those numbers represent height measurements or an image pixel. And of course, by experiencing both ends of the spectrum, both the theory and the implementation, and then finally plugging data into your model, that's going to make you very well-rounded professionally. To conclude this lecture, I want to pose a final question. How does all this knowledge help you? Why does understanding the approach of this course make you better at machine learning in general? Well, my hope is that this gives you a very high-level, bird's-eye view of the landscape. You can see the different approaches of people from different backgrounds. Academic people typically don't see what other non-academic people are doing, and those people who hate math typically don't see what people who love math are doing. So with this bird's eye view, you can see everybody. If you're learning machine learning, it helps you understand who am I competing with when I apply for a job, and what kinds of jobs are out there, and what would be adequate preparation. If you're hiring for a machine learning team, it helps you understand the different backgrounds of individuals you have to compare to one another to understand their strengths and weaknesses and what they bring to the table. In this lecture, I'm going to talk about Jupyter Notebook. Occasionally, I get this strange question from students asking why I don't do things in Jupyter Notebook. Let me explain why I think this is strange. Firstly, it's my position that it's completely unnecessary and actually doesn't change anything to use Jupyter Notebook or not. Let me repeat that. Using Jupyter Notebook is exactly the same as not using Jupyter Notebook. There's no difference other than the fact that it looks different. In other words, the screen is a different color. Obviously, such a difference is trivial. In this lecture, I'm going to demonstrate how that's the case. One major reason I dislike Jupyter Notebook is because it causes too many students to be unaware of how Python really works. If you're only comfortable inside Notebook, and when you see Python code in a text file or anywhere else, and you get scared or intimidated, that's not good. That Python code that's in the text file is exactly the same as what would be in the notebook. There's really nothing scary about it. Programmers working at real jobs eventually need to write code that's going to be deployed and run automatically. In other words, your final code is going to sit in a Python file that runs by itself without Jupyter Notebook. So if you're going to have any hope of using these skills in a real job, you had better be comfortable with writing Python code outside of Jupyter Notebook. You would also better be aware that there's actually zero difference between writing code in a Jupyter Notebook and writing code in IPython or the console. Here's one example I like of how you might use Python in the quote-unquote real world. Let's say you write a script that emails your boss to tell him you're going to be late for work. And let's say you don't actually want to send this email manually, but you want it to get sent automatically every Friday morning so that your boss doesn't yell at you for coming into work late after you had partied too hard Thursday night. Well, that's very simple. All I have to do is, on my server, create what's called a cron tab. In it, I just enter the code for when I want this command to run, and then to the right of that, I specify the command that I want to run. That's just Python space and then the script name. As you can see, it's simply how you would run this Python script from the command line. And now, every Friday at 9:45 a.m., this script is going to send the same email to your boss to tell him you'll be late. Well, let's not get off track here. The point of this is, you really don't want to be using Jupyter Notebook for something like this. I think one perceived advantage of Jupyter Notebook is that you can see the results of intermediate calculations. However, this is merely a perceived advantage and not a real advantage, because you can do the exact same thing even when you're not inside Notebook. Firstly, as I'm sure you've seen by now, IPython also prints out the results after you enter a command. IPython is called a REPL, which stands for Read Eval Print Loop, and that's generally what they all do, no matter what language you're in. So whether that's Python, Ruby, PHP, or any other language. The keyword here is print. Why is that? Well, one of my golden rules for writing and debugging code is when in doubt, print it out. I can't tell you how many times I've gotten a question on the Q&A when it could have been easily answered by inserting a print statement into the existing code. Anyway, what's the point of this long discussion about printing things out? Well, it's that if you think Jupyter Notebook is the only program that helps you do this, you need to expand your horizons a little bit. You should, in fact, always be doing this. If you're not using an abundant amount of print statements while coding, you are not doing it right. Remember, programming is not philosophy. You're not supposed to be running a program in your head. That's like trying to do long division in your head when you have a calculator in your hand. So just by printing things out, you can be more efficient. Stop trying to guess what a program will do, and just let the program itself tell you what it's doing. The key takeaway here is, you should always be printing things out. The fact that Jupyter Notebook shows you the result of each block of code is not simply a happy surprise. But another important lesson here is that if you want to use Jupyter Notebook, there's absolutely nothing stopping you from doing so. In other words, using Jupyter Notebook is 100% compatible with everything we are already doing. In fact, if you recall, your goal in these courses is not to run my code, but to write your own code. And of course, since it's your code, you can write it however you want, including Jupyter Notebook. In the rest of this lecture, I'm going to prove to you that you can take any script from our course repository, which we know runs in the console, because that's how I always demonstrate it, and show you that this exact same code runs in Jupyter Notebook. Let's begin. Okay, so let's say I'm in the folder Numpy class, and I'm interested in the code inside classification example.py. As you can see, what I have right now is this code inside a text editor. Now, if you're not aware of what a text editor is, it's just a program that shows you the contents of a text file and lets you edit those contents. It's the ideal program for writing code. Now, occasionally, if you're writing in a language like Java or Swift, you might want to use an IDE, but even then, it's totally optional. These days, I prefer to write Java in a plain text editor like Sublime Text as well. In any case, normally, one does not need to use an IDE for writing Python code. Now, about Jupyter Notebook. Well, let's start up a Jupyter Notebook. So I'm going to go Jupyter Notebook. All right, so now I've got Jupyter Notebook running, so I'm going to start a new notebook. Also, notice that we started the notebook in the same directory as the relevant Python file. So that's something you want to keep in mind for the future. Now at this point, what I'm going to do is, I'm going to prove that everything in this Python file works exactly the same in the notebook as it does in the console. So let's start with the imports. Actually, let's grab this one too. All right, paste that in, run it. So everything's fine so far. Now let's load in the data. Okay, we've loaded in the data. Now I'm not sure what its type is, so I can check it by using the type function. So let me try that. Cool, so I get sklearn.utils.bunch, so that's the type of the variable data. Now previously, you recall that we did this example in IPython, but as you can see, the result is the same in Jupyter Notebook. Alternatively, if you wanted to run this Python file in the console, so you wanted to type, let's say, you wanted to type in Python classification example.py, then you could just add some print statements if you wanted to show those same lines while this file was running. Now, I'm not going to go through such elaborate detail for the rest of this example since you've already seen it, so let's just get through the rest line by line. Let's say I want to check out the keys in the data variable. Okay, looks good so far. let's check the shape of the data attribute. Okay, looks good so far. Let's check the targets. Okay, still what we expect. The target names looks good. Target shape. This should be 569, yep. And let's check out the feature names. Okay, that's the same as well. Now let's do our train test split. Okay. Now let's instantiate and fit our model. All right. Now let's check the train score and the test score. All right. Now let's see how we can make new predictions. So you see how if you assign to a variable, it doesn't print the result. But if you have an expression, then it does print the result. So those are some predictions, and this was an alternative way to calculate the accuracy of the predictions. So we get the same answer as before. And we also have this other example where we can use a neural network to do the same thing. So let's build the model, train it, and print the train score. And let's print the test score as well. All right, so everything works the exact same way as it does without using Notebook. Now, another thing I could have done was I could have just taken this whole thing and copied it and pasted it in and run it. So that's another possible thing you can do. But the downside of that is you don't get to see the intermediate outputs. But again, that's what print statements are for. All right, so what can we conclude from this exercise? Well, we can see that this code runs exactly the same inside Jupyter Notebook as it does everywhere else. That's why I always say Python code is Python code no matter where it is. If you want to use Jupyter Notebook to run the course code, there's absolutely nothing stopping you from doing so. Hey everyone, and welcome back to this class. This is a short lecture to explain that you are free to use whichever version of Python you want in this course. Just one side note before we begin. While I've updated all the code in the repository to work with Python 3, you still need to git pull to ensure that you have the latest version. I know that some people fork the repo on GitHub, but I strongly recommend not doing this as you won't get the latest updates as easily. If you do have a fork, consider just getting rid of it, or at least make sure you pull the latest changes often. A lot of people consider Python 3 to be the new version of Python, and therefore it's the one everyone should use, but that is a very limited perspective. First, Python 3 is actually not that new. In fact, at the time this lecture was made, 2018, Python 3 is almost 10 years old. In fact, Python 2.6 was released at the same time as Python 3. So Python 2.6 and Python 3.0 are actually the same age. Some people think that because 3 is a bigger number than 2, that means we should use 3. Of course, you can see why this is a somewhat superficial way of reasoning. The bigger issue is this. If you join a large company using Python today, and they built their technology stack many years ago, they are probably using Python 2. And if you're in a large company, it's not easy to just recreate your entire codebase. That might take months or years of effort. No reasonable company that makes millions of dollars per day is going to halt their operations just so they can switch Python versions. Consider your choices if you are a manager or a business owner. You have a list of things to get done. Your clients want these things done, and they're going to pay you lots of money to get them done. So if you have a choice between your engineers working on something that will make money versus working on something where you not only get paid no money, but that actually costs you money because you have to pay the engineers to do the work, which are you going to choose? Most people I know would choose the option to continue making money. And so for better or worse, a lot of folks are still using Python 2. That means if you join such a company, you'll be forced to learn Python 2 syntax. There will simply be no way around you having to learn Python 2. At the same time, the differences between Python 2 and Python 3 are usually trivial. For example, instead of print with a space after it, print works like a function, so it has to have parentheses. Another example is that we use range instead of xrange, which both return generators rather than lists. In Python 2, range returns a list, which can be inefficient, so we try not to use that when we're using Python 2. In Python 2, division using a slash can do different things depending on what its arguments are. So for example, if both the numerator and denominator are integers, then the result will be an integer. But if at least one argument is a float, then the result will be a float. This is the same way division works in C-style languages, so it's pretty typical behavior. In Python 3, a slash always does float division, so even if your numerator and denominator are both integers, the result will be a float. If you want to do integer division, you have to use a double slash. Other examples are given on this page on my website, lazyprogrammer.me/Python 2 to 3 tips. Of course, aside from these things, there are a lot more less frequent discrepancies you may come across. So if you come across something that doesn't work, you're encouraged to use the Q&A since that is the best place for you to get help. However, you most likely won't need help since the changes are trivial 99% of the time. So there's no need to give up if you see that the code you're working with is for Python 2 and not Python 3. Most likely, just a few lines need to be changed as per the error messages you get, and you'll be up and running in no time. Hey everyone, and welcome back to this class. I created this lecture to answer a question I've been getting a lot recently. As you may have heard, Yoshua Bengio recently announced that development on Theano is going to stop after version 1.0. I posted about this on my website, lazyprogrammer.me, on September 29th, 2017, in case you want to go check out the post. A lot of people have interpreted this announcement to mean that Theano is dead. I think that's a bit of an overstatement, and in this lecture, I will explain why. So first, let's talk about why Theano is not quite dead. Well, if you go over to their GitHub page, you'll see that their latest release is in fact 1.0.1. So if you were thinking they hit 1.0 and just dropped everything, you can see why that is not quite right. As of the end of 2017, the latest version is 1.0.1. We have yet to see if there will be releases after this. Secondly, consider what version 1.0 being released really means. In these modern days of open source software, developers are generally very conservative in their numbering. You'll see projects in version 0. something for years, even when there are huge communities around them. Case in point, the latest version of Numpy as of the creation of this lecture is 1.14. The latest version of Scipy is 1.0. The latest version of Pandas is 0.21.1. The latest version of scikit-learn is 0.19.1. These are all libraries that we have been using extensively for years, and half of them haven't even reached 1.0. So the fact that the developers of Theano thought their project deserved a 1.0 release is a huge milestone. This is in fact the most perfect version of Theano that has ever existed, so why not make use of it? It's also important to keep in mind that this is software. Software is code. Code is not like a car, for example. If you don't maintain your car, eventually it will fall apart and it won't work anymore. Code is not like that. Just because you don't maintain your code doesn't mean it stops working. So rest assured, you don't have to be afraid that no one is maintaining Theano. It's not going to break on you. Also keep in mind that pretty much all of the modern deep learning libraries you see today, not including Theano, are heavily inspired by Theano. There are some differences, but many similarities. As you can probably tell from my courses, I am mostly concerned with fundamentals. What do I mean by that? Well, as an example, I believe that in order to teach someone how to add, you have to teach them a fundamental understanding about addition. You can't only teach someone how to memorize 1 + 1 = 2, 1 + 2 = 3, and so on. Addition is a great example because there are an infinite number of possibilities you can have when doing addition. In fact, it is impossible to understand unless you know the fundamental principles. I believe learning all things should be the same way. So when you learn Theano, it's not about the syntax. It's about learning the basic fundamentals of how Theano does things. It's very different from regular Numpy programming. You are not programming with numbers, you are programming with variables. So when you write an assignment statement like A = B + C, you're not assigning the values of B + C into A. In Theano, B and C don't have any values, so that statement doesn't make sense to begin with. Instead, all you're doing is telling Theano how A is to be calculated in the future when you give it values for B and C. That's a fundamental principle that carries over to TensorFlow, PyTorch, CNTK, and so forth. So learning Theano is not about memorizing syntax. It's about understanding these fundamental principles. They easily carry over to other libraries, which are similar in many respects because they were inspired by Theano. Also keep in mind that most deep learning libraries came out much later than Theano. They are still in their very early stages of development. In some cases, that means they don't even have a lot of features yet. For example, array indexing. Easy to do in Theano, not so easy or impossible in other libraries. I go more in depth about these differences in my Theano versus TensorFlow lecture in Deep Learning Part 2, otherwise known as Modern Deep Learning in Python. So if you're looking for a certain special functionality, be mindful that the library you're working with may not even include it to begin with. Another important fact that I've repeated before is that Theano is a great learning tool. It's absolutely fantastic for learning how to code neural networks. This is mainly due to the fact that the syntax in Theano looks a lot like the math you see on paper. As an example, let's look at the equation for a neural network layer and compare it to Numpy syntax and Theano syntax. So not only does it look like the math, it looks pretty much exactly the same as Numpy, which is great because you already know Numpy. So it's very easy to go from Numpy to Theano. The syntax is essentially the same. As an anti-example to this, let's look at some CNTK code. So here's the code for creating the neural network layers and specifying the cost. Here's the code for the training loop, which of course isn't an actual loop because the loop happens internally. So out of this 100 lines of code, where can we even find the equations for a neural network layer? They are in fact nowhere to be found. Let's look at this code for loading in the data. We can see how unintuitive this looks. It's not clear what format the data has to be in for these functions to work, nor is it clear how we can customize these functions for different types of data. This isn't to say that CNTK is bad, I just picked a random example. But it just goes to show that, compared to Theano and what we know about scikit-learn and NumPy, It's not easy to go from one to the other. The most important drawback, however, is that this code bears almost no relation to the theory and algorithms we discuss in deep learning. Theano is nice because there is a smooth transition from math to Numpy to Theano code. It all pretty much looks the same. Everything you see in the math and the pseudocode happens in the actual code. With libraries like this, you end up looking through documentation and trying to figure out what is the right function to call. And as I mentioned before, it may not even exist. So you'll just be looking and looking forever. Finally, let's look at this from a practical standpoint. I use this same example in my lecture about Python 2 versus Python 3 because it's a real example, and if you encounter it, you have no choice but to conform. So consider the situation where you're in a large company making millions of dollars. Clients are paying you to add functionality to your existing product. The more stuff you make, the more money you make. Think about how unreasonable it would be to tell your clients, hey, I'm going to stop working on some stuff I promised you because the devs want to recreate our neural networks in TensorFlow instead of Theano. That sounds ridiculous. To the client, there's no visible effect. As a client, it sounds like you're telling me you want to spend months writing code so that you can replace a neural network with another neural network that gives me the exact same result as the old neural network. Well, firstly, you're not getting paid for that. So your choices are the following. Number 1, continue building with what you have and make money. Or number 2, let your devs spend a lot of time rewriting code that is invisible to everyone except them. Do not get paid anything for it, and in fact lose money because you still have to pay those devs. As a manager or business owner, the choice seems obvious. Continue making money. So the point is, if you're joining a team who has already built their stack using Theano, then that's what you'll continue to use. If their systems are using Theano and they require debugging, you'll have to know Theano very well in order to debug the code. Saying, stop your business for 3 months so we can rewrite all your machine learning code is an unreasonable prospect to say the least. So I hope this lecture has convinced you that immediately shying away from Theano upon hearing that development has stopped is a bit of an overreaction. I hope you can understand the many positives of working in Theano, including how it can actually aid you in learning about deep learning. Hey everyone, and welcome back to this class. In this lecture, I'm going to answer a question that I get pretty much multiple times per day, and that is, what order should I take your courses in? This is a great question, and it's something that even I have to think about sometimes. What is the best way to learn all this stuff? So I think that what you'll find is, this ordering makes a lot of sense in that we're always building on skills we learned before. So it's just like learning calculus. First you learn calculus 1, then you learn calculus 2, which is kind of the opposite of calculus 1. Then you learn calculus 3, which expands on the ideas from both calculus 1 and 2. And then from there you can go on to even more advanced topics like probability. So this is a process based on skill building. Now it's important to keep in mind that this lecture is not just about my courses and how to navigate them, although that is the question I'm answering, since that's a question I get multiple times per day. But this is also a lecture on how different machine learning topics are related and what depends on what else. So even if you end up not taking any of my courses, it doesn't change the fact that these topics are still related to each other in these ways. So in some sense, this lecture isn't really about my courses at all. It's a general lecture about how different types of machine learning models are related and in what order you might want to learn them from a skill building perspective. Now I want to show you this stuff in a visual way. I've actually set up a web page where you can go to and look at the chart I made for yourself. So what I want you to do is go to this website, deeplearningcourses.com. Now I want you to click on the catalog link. And from there you want to click on the click here link. Okay, so this brings us to the course order web page. So at the top you have sort of this linear chart, right? It's just one course after the other after the other. But this is not really what I want to look at in this lecture. This linear chart gives you a basic overview, but it's not ideal. The reason is, the relationships between courses are way more complex than this. Sometimes one course gives you the skills you need for 2 other courses. Sometimes there will be a course that's so complex that it depends on multiple different courses. So this is the perfect opportunity to use a graph. So if you scroll up at the top, you can use this link to just jump down to the bottom, and we have this graph where you can see the dependencies between each course. So what I'm going to do is I'm going to go through each link in this graph and explain to you why it exists and why it's important. So let's look at the SQL course first, since that has no links. So it might show up in the middle, so you can just drag it out to the side. That's the coolest thing about this graph, because you can just pick stuff up and drag it around. It's very interactive. So SQL has no links. This isn't a prerequisite to any other course, nor is any other course a prerequisite to it. It is standalone. You can take it at any time. Next, you'll notice that there are courses that have no links going into them. So for example, the Numpy course. This is because none of my other courses are a prerequisite to this course. This course was just designed to give you a basic understanding of the syntax and tools we use in data science and machine learning. The goal is actually to not do any machine learning in this course. Believe me, it was actually quite difficult to accomplish that because it's so easy to use something in machine learning as an example. It was very hard to avoid talking about it. You'll also notice that there are some courses with no outgoing edges. You can think of these as the most advanced courses. They are at the top of the ladder. So for example, this one right here. Of course, that could change in the future as I create more courses, in which case I will update this lecture. So let's start with what's coming out of Numpy. You'll see that there are 2 links. One goes to linear regression, and one goes to Bayesian machine learning A/B testing. And by the way, you can zoom into this graph, so that's what I'm going to do right now. Okay, so here's linear regression, here's Bayesian machine learning. So while Numpy goes to both of these courses, I'd actually strongly recommend linear regression as the next step. Bayesian machine learning doesn't depend on any other courses per se, but it's still more advanced. It requires a more advanced understanding of probability and of real-world engineering problems like optimizing the click-through rate of a link on your website. So linear regression would be my #1 recommendation for your foray into machine learning. Now after linear regression, we have logistic regression. So why do we go from linear regression to logistic regression? Well, the basic idea is both of these are linear models. In other words, the model is of the form y equals mx plus b, which is a line. The difference is that linear regression does regression, while logistic regression does classification. We want to learn classification because that's one of the central tasks of a neural network, which is what comes after. Now you might notice that linear regression also has 2 outgoing links. So there's one to logistic regression and one to reinforcement learning. This is because my reinforcement learning class makes use of linear regression, so naturally, if you don't understand linear regression, you won't understand that part. But again, this is a much weaker link than going from linear regression to logistic regression. This is because reinforcement learning is actually conceptually more difficult. It doesn't depend on the content of any other courses directly, other than what we've shown, but the ideas behind it are more advanced. You really want to have some experience with both supervised and unsupervised learning before jumping into reinforcement learning. It helps to build the proper perspective on the subject. We will get back to reinforcement learning later, but for now, let's go along the deep learning path. So on the deep learning path, we last discussed logistic regression. This is also known as a neuron. This is very important because in order to build a neural network, we must first know how to build a neuron. A neural network is just a bunch of neurons stuck together. So this leads us to Deep Learning in Python Part 1, which is the bright green logo. This course teaches you how neural networks work and basic fundamental operations like backpropagation. Once you know the basics of deep learning, you can move on to Deep Learning Part 2, or Modern Deep Learning in Python. This is the same image, but in a darker color to signify that it's a continuation of the previous course. As the title suggests, this course is all about modern developments in deep learning. So we go over ways we've improved basic backpropagation, like momentum and adaptive learning rate techniques like RMSprop and Atom. We talk about modern regularization techniques like dropout and batch normalization. And most importantly, we look at modern deep learning libraries like Theano and TensorFlow. We also take a look at Keras, PyTorch, MXNet, and CNTK. You'll see that once you know the fundamentals, things don't change that much from one library to the next. It's all the same concept. Now, learning about these modern libraries sets the stage for the next level, which is applying deep learning to certain special data formats. The two fundamental types of data are text and images. These are special because they have unique structural properties, and we can make use of our knowledge of those properties in order to build better neural networks. For example, we know that text is made up of sentences, and sentences are sequences of words, so sequential modeling is important. We know that images are two-dimensional objects, but importantly, each pixel is very likely to be the same as nearby pixels. For example, if you pick a random pixel on an image of a red car, if that pixel is red, then most likely the pixels around it are also going to be red. There is also no question about the practical applicability of text and images. The internet is made up of text, so by doing machine learning on text, you're learning techniques that essentially allow you to write models of the entire world's knowledge. Images are also everywhere. Snapchat, Instagram, Facebook, self-driving cars, home security systems. Knowing how to deal with images is super important, and billion-dollar companies exist because they are good at it. So that brings us to the next course in the deep learning series, Convolutional Neural Networks, or Deep Learning in Python Part 3. This is all about how to incorporate convolution into neural networks and what convolution is in the first place, and how that helps us make use of the structure of images. Let's scroll up a bit. So after convolutional neural networks, we take a detour into unsupervised deep learning. Unsupervised deep learning isn't very popular with beginners, but it should be. If you look at the experts of deep learning like Yann LeCun, Yoshua Bengio, and Geoffrey Hinton, they all talk about how important unsupervised deep learning is. This course introduces us to several new ideas. First, the idea of latent variables or latent causes. These are factors that you don't directly observe in your data, but that you can learn about by studying the structure of your data. Second, modern techniques for data visualization like t-SNE. This will be very important since, as I discussed earlier, along with images, text is a really important data format. In order to visualize text in later courses, we will be making use of t-SNE, so it's good to know what it is and why it's useful. Third, unsupervised pre-training. Unsupervised pre-training is the foundation of modern ideas like transfer learning, and we make use of it both in NLP and with convolutional neural networks. Fourth, the vanishing gradient problem. We demonstrate the vanishing gradient problem directly so you understand where it comes from. Vanishing gradients are especially important in the context of recurrent neural networks. And it just so happens that recurrent neural networks is the next course in the deep learning series, Deep Learning in Python Part 5. So recall that our two fundamentally interesting data types are text and images. We've looked at images, and in this course we start to look at text. Why might that be? Well, recurrent neural networks specialize in modeling sequences, and text is just a sequence of words, so it's the best type of data to use to demonstrate the principles of RNNs. Once we've studied RNNs, we can go even deeper into how deep learning can be used on text. That's the next course, Natural Language Processing with Deep Learning in Python, or Deep Learning in Python Part 6. In this course, we look at a very important concept called word embeddings. These allow us to turn words, which are categorical variables, into vectors, which are numbers that a neural network can read. This is why it's very important to have studied unsupervised learning before this, because finding word embeddings is actually an unsupervised task. Word embeddings also allow us to make use of pre-training, which was discussed in Deep Learning in Python Part 4. In this course, we also look at a very advanced model for doing sentiment analysis, called a recursive neural network or a tree neural network. This is an example of a dynamic neural network because it changes its structure based on what input you give it. Most deep learning libraries are not equipped to handle dynamic neural networks, and I demonstrate what happens if you try to build one the naive way. You basically end up building a separate neural network for each of your training samples, and it's going to eat up all your RAM and make your computer slow down to a crawl. So you get a first-hand perspective of why working with dynamic neural networks is not easy. But luckily, we are able to make use of our knowledge of recurrent neural networks, and remember that's the prerequisite to this course, in order to convert a tree into a sequence, which an RNN is capable of handling. So that's why RNNs is a prerequisite to this course. Now you'll notice that this course, Deep NLP, has no outgoing edges. This is because it's the most advanced course that I have on this path for now. I certainly plan on expanding in this direction in the future. However, this is not the last deep learning course in the series. After this, we have deep reinforcement learning, which is Deep Learning in Python Part 7. With that said, I think now is a good time to go back and start exploring the reinforcement learning path. So you'll notice that I have Bayesian machine learning feeding into reinforcement learning. On the surface, these two courses might seem unrelated, but there is a very important concept you'll learn that applies to both, called the explore-exploit dilemma. In Bayesian machine learning, you learn this idea in the context of trying to optimize a click-through rate or a conversion rate, or in other words, the number of times people buy things from your website versus the number of times people visited your website. Very practical concept, I think, if you do anything related to e-commerce. Now, in reinforcement learning, we look at the explore-exploit dilemma again, but in the context of playing games. Reinforcement learning is like a third branch of machine learning, whereas the other two are supervised and unsupervised learning. The main difference is that supervised and unsupervised learning look at static data. In reinforcement learning, the idea is more like you have a robot living in the real world. It can take the experiences it had today, and based on them, behave more intelligently tomorrow. So the learning paradigm in reinforcement learning is sequential. This is opposed to supervised and unsupervised learning, where your dataset usually resides in some file on your hard drive. So in reinforcement learning part 1, we get all the basics, as you might expect. This is a prerequisite to deep reinforcement learning, since deep reinforcement learning applies those concepts to more difficult games. But you'll notice that this is not the only prerequisite to deep reinforcement learning. As the title suggests, this is also dependent on knowledge of deep learning, in particular, convolutional neural networks. But as we know, in order to build a CNN, we have to know how to build a regular neural network, which means we have to know what a neural network is and why it's useful, and so on. So in deep reinforcement learning, these two paths converge. You combine your knowledge of both reinforcement learning and deep learning in this course. Now the reason it depends on CNNs and not, say, RNNs, which is over here, is because we'll be learning to play visual games. So, for example, we can learn how to play a video game like Pong or Breakout, which are classic Atari games from the old days. And so those are images because they're basically screenshots from the screen. In the future, we might end up applying RNNs, in which case RNNs will become a prerequisite to that course. So that's the end of the reinforcement learning path for now. I'm very excited to bring you more updates in this area in the future. Let's now jump back to logistic regression, where we can see another outgoing edge to supervised machine learning. So why is this edge here? Well, you may recall that linear regression and logistic regression are both linear models that do regression and classification respectively. These are both supervised learning tasks. And so it makes sense that now that you know one model for regression and one model for classification, it's time to dig deeper into supervised learning. The thing with linear regression and logistic regression is that they aren't really different models, they are both just a line. Because they do different tasks, the techniques and interpretations are slightly different though. And there are, of course, different models that are not linear models that can do these tasks, and that's what this course is all about. In this course, we look at classic supervised machine learning techniques like k-nearest neighbor, decision trees, the perceptron, and the Bayes classifier. Much like how logistic regression was the basic building block of the neural network, classic models like decision trees are the basic building block of ensemble methods. So that's why this course is a prerequisite to ensemble machine learning. Again, we use the same logo with a different color to signify that these two courses are very closely related. In ensemble machine learning, we learn how to combine multiple decision trees in different ways in order to make some very powerful classifiers. What's really remarkable about these methods is that they are very easy to plug and play on data. So if you're looking for a plug and play solution without having to learn a lot of theory, then deep learning is most likely not for you, but ensemble methods are a great fit. Deep learning is very dependent on hyperparameters, and if you choose incorrectly, your model will perform very poorly. Sometimes it requires immense computing power to find good hyperparameters. This is an active area of research. It is not yet solved. This is why you can implement what you see in a deep learning paper, but suppose the author left out some seemingly insignificant detail, so you end up having to make an assumption, and then your results end up totally different. So deep learning is fragile. But luckily, ensemble methods are not. We focus on two very famous ensemble methods, the random forest and AdaBoost. So that's everything on the supervised machine learning track for now. Next, we see an edge going from supervised machine learning to unsupervised machine learning, in particular cluster analysis. The reason we study supervised learning before unsupervised learning is because unsupervised learning is a little more abstract. It takes more effort on the student's part to realize why it's practical and what it can be used for. Cluster analysis shows us how to model data that does not come with targets. As you might guess, we do this in the form of clustering. The idea behind clustering is very simple. We want to know how many naturally occurring groups of data there are, and what are the relationships between the data in these clusters. So for example, if you were clustering books, you might find a book about Steve Jobs and a book about Elon Musk in the same cluster. This cluster is probably about tech companies in Silicon Valley. But you don't need a label in your data to tell you that. You can discover it yourself by looking at how the data naturally groups together. Now, as I mentioned earlier, I think once you learn about both supervised and unsupervised learning, you'll be ready to jump into reinforcement learning. I haven't made cluster analysis a prerequisite to reinforcement learning since none of the material depends on this course, but it's good to know about these techniques so that you have a more mature and experienced view on machine learning. What is sort of a sequel to cluster analysis is hidden Markov models. The reason might not be clear at first, so let me give you two reasons. Number one, they are both unsupervised machine learning models, just that HMMs is harder, so it's natural to learn about clustering first. Clustering is also about static data, whereas HMMs are about sequences, so it's similar to the process we did in deep learning. We looked at static data like images, then sequential data like text. Reason number two, in cluster analysis, we learn about a technique called the Gaussian mixture model, which we make use of in the HMM course. One key point is they both learn by using the expectation maximization algorithm. So it's good to first see the EM algorithm on a simple model, and then when you see EM again on a more complicated model like the HMM, it won't be as intimidating. One key concept you learn in HMMs is the Markov assumption. That just means the current state depends only on the previous state, but not any states before it. This is a simplifying assumption that usually makes the math easier to work with. You will also notice that we encounter the Markov assumption in reinforcement learning. However, it's not too hard to learn it from scratch. And so for that reason, I do not consider HMMs to be a prerequisite to reinforcement learning. The Markov assumption is really the only thing they have in common. There is also a slight connection between cluster analysis and unsupervised deep learning. So I'm not going to draw the link right now, but I sometimes consider this to be unsupervised machine learning part 1 and this to be unsupervised machine learning part 2. We also see that HMMs feeds into the RNN course, which is about deep learning. So why might that be? This is of course because both these models are models that can learn about sequences. In particular, in both these courses we model text as sequences. But whereas the HMM makes use of the Markov assumption, the RNN does not, and hence the RNN is a more powerful model. And so this just goes along with the main theme that we always go from simple basic models to more complex models. This is also something you should do in your work as well. If you start with a simple model, you often find that it is faster and more robust. Complex models sometimes break down, but they are also more difficult to implement and might not even be fast enough. Of course, that's just a generalization, so you always want to analyze engineering trade-offs individually for every problem you have. Now, there is one last link in this part of the graph here that I want to explain, and that's the first NLP course. You can see that it depends on supervised machine learning and feeds into deep NLP. The main purpose of this basic NLP course is to apply basic machine learning models to text. So that's why supervised machine learning comes before it. It's because that this course was all about basic machine learning models. The important skill for NLP was not the implementation of those models, but rather a bigger picture perspective on how machine learning is used. What is the interface between the data and the model? What does the model do? What is its input and output? How is the output interpreted? And so we take those principles and we apply them to text. In this way, we can see that text can be treated in such a way that you don't have to think about it any differently than any other data. This reinforces the principle that all data is the same. The machine learning model doesn't care what your data is. All it sees is a table of numbers. It doesn't care if it's text or images or radar signals from space. The model just does what it was designed to do on the numbers that you give it. So this course gives you a high-level systems perspective on working with machine learning models in text. This easy NLP course also feeds into deep NLP, which is of course not so easy because it depends on a lot of background in deep learning. One of the main questions I get in the NLP course is, how do I improve the results of these basic models? And a lot of the time the answer to that is, well, you have to use a more complex model, but of course that necessitates learning how that complex model works. And deep NLP is an example of that because we learn a state-of-the-art method for sentiment analysis, whereas in easy NLP, we used only a linear model. So it's important to understand that while yes, it's possible to improve the predictive ability on simple basic models, as you can see, it's not always an easy path to get there. So you have to make sure you're prepared. Case in point, just look at all the time spent just to get to deep NLP. It's not an easy task. Let's now scroll over to GANs and variational autoencoders. Just like how deep reinforcement learning is not related to deep NLP, this isn't really related to deep reinforcement learning either. This is Deep Learning Part 8 by order of creation only. It is the spiritual sequel to unsupervised deep learning, which was Deep Learning in Python Part 4. Okay, so just to reiterate, this is Part 6, Part 7, and Part 8 by order only, but they are not related to each other conceptually. Although it's always nice to know all these things because more context makes future things easier to learn. So the reason this is linked to this is because GANs and variational autoencoders are also unsupervised deep learning models. But whereas unsupervised deep learning was all about how to improve supervised learning, GANs and variational autoencoders don't have any direct benefit to supervised learning at all, although we do make use of supervised learning within the course. In this course, the focus is on generating images. We've seen that GANs can create photorealistic images based on a dual neural network system. That's pretty cool because before GANs, we didn't have any kind of machine learning model that could generate real-looking images. Nowadays, GANs are able to generate high-resolution, high-quality images of people that you can't even tell are not real people. It certainly makes the idea of the matrix seem very possible. Alright, so I hope you found this lecture helpful. We saw that these courses are related to each other in some pretty complicated ways. Learning machine learning is not exactly linear, Sometimes you have to take one course before you can take the next. Sometimes one course might just be related to another course by some key concept, but maybe in one context it's a lot easier to understand. So remember to keep in mind that these arrows do not all indicate strong prerequisites, but rather there's just a relationship between the two courses. I hope that this lecture explained any nuances between what is a prerequisite and what is not, and I hope I did a good job of answering which order should you take these courses in and why.